Welcome to the lecture on logistic regression. This is used for classification purposes. That is, suppose if we have x as input and y as output. So based on every input, we just have two values of y if it's a simple classification problem. For example, if x is CGPA, y can be just is the student placed or not. Another day-to-day problem which we usually use is spam email problem. So once we get some input email and Gmail has to decide whether it is spam or not. So something being positive, something being present there is called positive class, and something not being there is called negative class. And it is customary to denote positive values by 1 and negative by 0. That is, if x is CGPA and student is placed, we will say y is equal to 1. It means student is placed. And if y is equal to 0, means student is not placed. Similarly, in case of email, if the incoming email is spam mail, then we will say the value of output is 1. If it is not spam, it is 0. What is the input in case of email? So spam is decided based on various parameters like the subject line, or inside the body it is written that you have $1 million and other things. So some suspicious text inside, or the suspicious subject, and similar patterns are being learned over time to detect that whether the email is spam or not. Now, contrary to linear regression, what was the hypothesis function we had in linear regression? Suppose we have just one variable, so it was theta 1x plus theta 0. Okay, and in case of linear regression, suppose x is CGPA. I will continue with that example, and this y which we denote by the hypothesis function is denoted here the average CTC. Now average CTC can take any value, so of course it will be positive, and it can have any value. It can have 1 crore, 2 crore, whatever. Now coming to logistic regression, can we use the same hypothesis for classification problems? The answer is clearly no, because theta 1x plus theta 0 can definitely will be greater than 1 also at times and less than 0 also. We need some hypothesis function such that, so let me write it here. So we need some hypothesis function which will be between 0 and 1. Okay, now see, we have only two classes. Suppose y is equal to 1 or y is equal to 0, but the hypothesis function can take value between 0 and 1. Now when to decide that, suppose x is CGPA and y is whether placed or not. Let's say we have data available. So CGPA something 7.9 placed, 6.5 not placed, 8.5 placed, right? Suppose we have such database. Suppose 9.6 placed and again 6.8 not placed, like that. Now again we will divide this whole data set into two parts. One will be the training part and one will be the testing part. And now coming to the training part, you see we have data that a particular student has this CGPA and is placed, another student has 6.5 CGPA is not placed, so on and so forth. So we need to find the model parameters. So what does it mean? First of all, we need to identify that the hypothesis function should be of what type. It cannot be linear for sure, for this obvious reasons. So what type of function it can be? For that, let's think in this way. So suppose x is again the CGPA and y is the that whether it's placed or not. Now what can we statistically say given the x? We can say what is the probability that a particular student is placed or not. So in that sense, let's frame the problem like this. Probability that student is placed is probability x is equal to 1. Oh, sorry, y is equal to 1, and let me denote this by p. And probability that student is not placed, and rather saying this to be 1, yeah, y is equal to 0. So it will be 1 minus probability y is equal to 1, which is 1 minus p. Okay, now we usually will compare the ratio of the two, and we say that probability that a student is placed divided by probability that a student is not placed Okay, if it is greater than some threshold, suppose z, then we will decide that student is placed. If it is less than some threshold, we will decide it is not placed. This is one logical way. Now it means that p divided by 1 minus p has to be compared with some threshold z. Okay, and it is very customary in case of such analysis that we will take log on the both sides. Okay, so log, and let's say this is z dash, because we need z for some other purpose. Log z dash, so let log z dash be denoted by z, so log of this. So this is called a log likelihood ratio, by the way. Now it means that p divided by 1 minus p we have to compare with e to the power z, because the base here is e. Okay, so when we see what is the form of p, so we'll get like this. So p 1 minus so e to the power minus z minus p e to the power z. So p we take here 1 plus e to the power z e to the power z. So it means that we need to compare this p with e to the power z divided by 1 plus e to the power z, which we divide numerator denominator by e to the power z. It becomes 1 by 1 plus e to the power minus z. So this is sort of a probability, that what is the probability of a student getting placed or not. Okay, definitely, since it is a probability, it will be between 0 and 1. Now this can be used as hypothesis function. How? What we will do is we replace this z by this theta 1x plus theta naught. Okay, this is important, so we replace it by this. And now you see, if you equate this by y is equal to h theta of x, which is equal to 1 divided by 1 plus e to the power minus theta 1x plus theta 0. Now whatever be the value of x, whatever be the CGPA, this value of h theta of x will always be between 0 or 1. What is the best way to decide whether placed or not? We say that if h theta of x is greater than or equal to 0.5, then the student is placed, because the value is near to 1. If h theta of x is less than or equal to 0.5, then the student is not placed, because value is closer to 0. In fact, if you plot this function 1 divided by 1 plus e to the power minus z, it looks like something like this. So this is 1, this is 0.5, and this function is a special name. It's called sigmoid function. Okay, this is very important function, and in the last lecture of neural networks you will see this is again appearing here. So now here is the setup. Now the hypothesis is denoted by, in case of logistic regression, 1 divided by 1 plus e to the power minus. So let me write here now theta transpose x. Suppose we may have multiple parameters now. So theta 0, theta 1 up to theta, suppose n, and similarly x is x0, x1 up to xn, right? So then this will be our hypothesis function. Now we have to decide first of all cost function. See, the thing is, h theta of x lies between 0 and 1, right? And y, the actual output from the training samples, has exact value either 0 or 1. So this y is actually here a y hat. Okay, so this is the y hat estimate of y. The actual y is between 0 and 1. So if you use mean square error, which is yi minus yi hat square 1 by 2m, I is equal to 1 to m. So this will not give you perfect loss function, because it will fluctuate. See, yi is fluctuating between either 0 or 1, 0 or 1, and yi is between 0 and 1. So this function is, in fact, will not have a convex behavior in that sense. If you use Python and try to simulate, you will get something like this. Okay, you can see that it doesn't have a global minimum. So we have to use something else, something smarter way to decide the cost function in this case. Now here is a smarter way to define the cost function. So Let's look at this. So h theta of x, which is defined now 1 divided by 1 plus e to the power minus theta transpose x. So this is something which lies between 0 and 1. And let's look the behavior of log function. Suppose log of x, you know that log function looks like something like this. So between 0 and 1, the value of log is negative. And if you take log of h theta of x, so this log of h theta of x will be negative. Now to make it positive, I will write here minus. Now what I am doing actually, you see, let's take two cases. If y actually is 1, correct? Now suppose your system or the model decides that h theta of x is closer to 0. So this is an error. The y actually was 1, but you have learned the model in such a way that your hypothesis function becomes closer to 0. This error. Another error is if y is 0 and your model decides that h theta of x is closer to 1. So these are the only two possible errors here because y is taking only two values. So in such a case, we will define a different cost function like this. So what should happen with the cost when you make an error? So cost should increase tend to infinity if there is error. Okay, and also cost should tend to 0 if there is no error, right? Now let's look at this, how we can incorporate log and this. Now suppose y is equal to 1. Okay, so y is equal to 1 and I want to define a cost function. So if I define a cost function like minus log of h theta of x, look at this. If y is 1, then if there is no error, what does that mean? That h theta of x will also be tending towards 1, maybe 0.8, 0.9 or so. So what is log of something which tends to 1? Okay, so it is 0. So that is what we want, cost is 0. Now if y is 1 but h theta of x tends to 0, tends to 0 means say it is 0.1, 0.01 or so, then looking at the graph, log of 0 tends to minus infinity, correct? And minus log of 0 will tend to plus infinity. So if y is 1 but your model decides it is 0, then we get minus log of 0 which tends to infinity. This is the cost function at that time, right? Similarly, if y is 0 but your model decides that it tends to 1, h theta of x, so in that case what should we have as a loss function? So it will be log of, just look at this, minus 1 minus h theta of x. See how? If your y is 0, that is a true value, but your model makes an error, it decides it is closer to 1. So now I take minus here also. So what will be the value of this? Log of 1 minus 1, but minus here. So log of 0 is minus infinity, minus log of 0 is plus infinity. So we get the cost plus infinity. And if again y is 0, but h theta of x also tends to 0, it means the decision is correct. So what will be its value? Minus log of 1 minus h theta of x tends to 0. So which is minus log of 1, which is 0. So the cost function tends to 0. And definitely we need to minimize the cost function. So definitely it will try to decide the model parameters such that cost function is. Now how to decide the cost function overall? See, the cost function we can decide like this, right, like this. So we write y times minus here log of h theta of x minus 1 minus y log of 1 minus h theta of x. See how is it cost function? Because there can be only two cases. Y is equal to 1. When y is 1, then this 1 minus 1 term is 0, second term is 0, so we get minus log of h theta of x. And in particular, if there is an error made by the algorithm, and that means h theta of, so y is 1 What can be the error? As theta of x is closer to 0, then this j theta of x will tend to infinity. Similarly, if y is 0, the first term will be 0, second term will remain. This is for one point in data set. So we recall that we have a data set like this. So x1, x2, xm and y. Oh, sorry, we have to write like this. Like in linear regression, we have x1, x2, xn. These are the input parameters for feature space. And first sample in data space data, this is 1, then x2, here also 2, then xm. So there are total m points in this data set. Then the cost function will be defined like this: j theta of x is equal to, so there will be minus y I log of h theta of xi minus 1 minus yi log of 1 minus h theta of h of xi, then summation I is equal to 1 to m 1 by 2m. So this is the loss function, cost function now. And the goal is to minimize j theta of x and then find the value of theta which minimizes this cost function. Will solve the problem. So some graphically, suppose how do we look at it? Suppose on the x-axis we have x, that is CGPA, and on y-axis we have just points. Suppose let's start with CGPA, of course 5. So then this is y, this is 0, this is 1. So suppose the low CGPA will not be placed, so we mark it like this, and abruptly at 7 CGPA students get placed like this. Very simple example. So this is how data set looks like, and we need to basically decide something called boundary, such that if x is greater than this, we get that has been placed. And you see, if you plot the sigmoid function over this, that will look like this. Okay, and to be more precise, maybe something like this. So as long as at this point this is the value 0.5, as long as h theta of x is greater than 0.5, we decide place it. Less than 0.5, we'll decide not place it. Okay, so this is the logistic regression, and this is actually, if we represent this unit as a circle, so this is the input x, and what is inside the circle? Inside the circle is this sigmoid function. It computes this function where z is equal to theta transpose x, and then you get the y decision, right? Y hat actually decision, whether it is positive or negative class, whether it is mail is spam or not, whether student is placed or not. This one unit of this logistic regression is also what models our neuron of brain. Now what is done in neural network, something called neural network, we basically have such units interconnected. Suppose we have two inputs, say x1 and x2. Let's say one is the CGPA and other is the grade of some subject, and then there will be inside several units. So the output of each unit is fed to another such unit, and then there is something called output layer. So there may be more units inside, and then we feed all the outputs to one unit again, and we get the output y. So neural network is nothing but a network of these logistic regressional units. You can take it in a very simple way. So if you understand logistic regression, you basically have understood a one unit of neural network. Now why is neural network so popular and strong? Because usually in logistic regression we just use one unit to classify, which is, and what is the one unit? It does a non-linear processing like this sigmoid function. And in when we make a network of this, the classification decision will be more logical, okay, it will be more strong, there will be less errors. That is what is expected. And this is exactly how our brain works. Whenever in our brain we get some signals, suppose from eye or ears, or so through any sensory organ, so that is first fed to some neuron, and then that neuron feeds to another neuron, and it does a lot of processing in between, and finally there is one neuron which takes a decision. Suppose you see some object with your eyes, then if the signal is sent to the neurons in the brains, then it is fed to different neurons which make a decision, and finally a neuron at the end makes a decision whether it is tree, or if it is person, or if it is whatever. So this forms the basis of neural network also. And one more last point I would like to say, see, the cost function has now this form, logarithmic form, and we know that log, if you remember, log of x, okay, sorry, there was some technical fault. So you see there is a log function here. Yeah, log here. So log we know is concave function. You see log of x is a concave function, so minus log of x is a convex function. So in that sense, if we look at this, so minus log of x term here and minus log of x term here, so two convex functions are there, so it is a convex function. So the cost function of logistic regression in this form is a convex function. So now the next video, possibly maybe last video, will be about neural networks, and then I will have a one Python implementation video where I will show together linear regression and logistic regression, how to implement.